Welcome. My name is Professor Wunderlich. I'm a professor of engineering, architecture, and computer science. This is a picture at Elizabethtown College you see in the background with me long ago, 23 years ago with Tom Leap. Before that, I was a professor at Purdue University. Before that, IBM Research, supercomputer design. Before that, AI DuPont Children's Hospital, rehabilitation robotics. Also was involved with neural network processors back then, and all during that time, designed two ones in the patent office. And then until I was 30, I was mostly in architecture. I'm 16 years old now, and coordinated all the design, engineering and architecture and construction, and some of the legal work too, of $100 million of real estate development and high-tech office parks in Texas and California. So now we're in a course, which is an introductory course. This is my website, so you can drill down into all the different things I do. The syllabi. So I've taught 38 different courses. I added up approximately 200 courses over the past 30 years, about 2,000 students. And we're in this course right down here, Computer Architecture and High-Tech Fundamentals. I also group on my webpage all the robotics and computer engineering and robotics, and you can click on the studio, lab, and all the symposiums and things we've done and the research and other stuff I've done. I was also a visiting professor in Italy, University of Trento in Italy, PhD course in robotics, advanced robotics, with a bunch of people from IBM and MIT and other places. And then I have a relationship with 7 universities now. Also work for the Italian government reviewing publications and grants. And I just sent a student to Italy, and she's in Italy right now. Sent another student a while back, brought another student another time. So I have a relationship there. Okay, so this is all the computer engineering things. We have our lab manuals and courses which have labs, not this introductory one. We're in this introductory course right here. And then these are the main computer engineering courses I teach: digital design, sometimes interfacing, sensory embedded systems, parallel processing, robotics and machine intelligence. So drill down in here where we are in this course. And make it a little bigger here. So there's 40 different things here. Now, I have MP4s and some of them on my YouTube channel from COVID times. I used to never put anything online. Now I have 200 videos on my YouTube channel. Just go there for a second, and for that to load up. Then you go to different playlists down here, high-tech lectures. I just posted this one. Go to playlists, and it breaks down into travel, high-tech lectures, high-tech student designs, architecture student design, architecture lectures. And then in the high-tech lectures, I've given priority to the advanced class that I'm teaching advanced computer engineering this year, so they're listed first. And then this is an introductory class, so you'll find those lectures down lower down here. I might start a whole separate play list just for this course, if I post enough on YouTube. Everything's also in our Canvas database, and I'll talk to that at the end here for the students. Okay, so we're in here. We're in here. Now I have the syllabus open. I'm going to open up again. Open up again. Should use the back button off of the to the YouTube channel. That's how I jumped from the syllabus. So they're in here, students. This was for a long time a required introductory computer engineering course for the computer engineering program. It was also required for all computer science and information systems students for a number of years, back 23 years ago. Now it's transitioning to an elective for computer engineers and then required for computer science and information system students, whereas it was just required for information system students and computer engineers until next year. We've already reviewed some of this stuff, and you can see a quick fly over of that in the MP4 on YouTube that I made for this tech history. And I'm not going to make a video of those because there's just certain specific things we're grabbing out of that. Today, I'm going to do conceptual architecture and levels of computing, microcontroller, microprocessors, robotics, and IBM quality controls. It's all intro stuff on my YouTube channel. I'll list it as intro computer architecture. So firstly, until now, it's just a PDF. So this is conceptual computer architecture. So you'll see me refer to this and also a minimal computer architecture, and I'll make clear the distinction. The conceptual is very conceptual. The minimal is something else. And if you just Google it, you're going to find different things on the internet. This is my own doing from back when I first started teaching long ago. So this is the basic concept you should just burn into your mind of overhead of what's going on on a motherboard. You have a central processing unit and some main memory. And of course, there's lots of other things that can go in here. And we'll talk about that in other detail in other lectures. There's a data bus. It's bidirectional because you have to read and write from memory. Then you have control lines. You're not really aware of those going on, but if you're designing hardware, you would be. And then there's an address bus. And it's only one way because you're addressing the memory. The CPU is addressing them. And I/O is not shown here for a reason. I'll talk about that. Scroll down here. So the CPU, it's the same diagram. The CPU, central processing unit, processes all machine instructions. This is not a high-level language, Java or C++ or Python. This is assembly language, one-to-one, machine code, which everything ends up. It doesn't have to go to assembly language, but assembly language maps one-to-one to machine code. Everything gets down in the machine code from your compiler or your assembler. And the processor, the central processing unit, process all that. It contains some fast access memory inside, and we'll look at that in other diagrams, the minimal computer architecture, not here. But there's memory inside the CPU too. There's also caches that aren't shown here. The main memory, we're just talking about the DRAM that's out here by itself. And we're not talking about storage either. Storage is your magnetic or optical drives or solid state drives. So the CPU contains some fast access memory, usually static RAM. We have a whole lecture on RAM we're going to talk about, or latches. So, and static RAM is different than dynamic RAM. Just quickly here, static RAM is faster, it's less dense, but it's more expensive. So you make your caches out of that, you make your registers on the CPU out of that, but you can't afford to make all the main memory out of that. And the dynamic RAM is cheaper. And so that's why you have more of that for main memory. So main memory stores machine instructions and data. And we've alluded to this a little bit here, talk about it more specifically in more advanced classes, but we mix together our data and instructions. And you don't really know where the difference is in the memory. You don't have to worry about that. And it's all put in one big memory for you, but it doesn't have to be that way. Some architectures, that's by the way, von Neumann architecture or Princeton architecture, where you mix your data and instructions together. The Harvard architecture, you have it separately, and we'll talk about microcontrollers in a second. There's reasons to put your code separate. Very quickly, the one reason would be because maybe it's a refrigerator or a fuel injector or an air conditioner, and the code doesn't have to change, but the data does, right? The temperatures and the actuations, feedback from the control loop. So that changes the data, but your code doesn't. So you burn in the code someplace and you have very little RAM on a single chip, and a microcontroller, everything together, not a motherboard. We'll get to that. So we'll learn in here about the machine formats coming up. We have operands. So the data being operated on is the operands, and then we'll look at an opcode coming up. That's what the instruction tells you what the instruction does, the opcode. And it's typically made from dynamic RAM, random access memory. And again, we're going to have a whole lecture on memory coming up. Then the bus is up here. So this isn't a bus like driving full of people kind of bus. This is a more analogous to the roadway. And so stuff's flying around on the buses. And so you have a data bus, 8 to 128-bit wide electrical pathway. Now we're not talking about graphics cards here, and you have wider pathways on graphics cards. That's a whole separate computer in itself now, since you own the graphics cards. Actually more powerful in many ways, lots of times, and where you do your AI and deep learning. But this data bus is bidirectional, exchange data between the CPU and memory, and exchange machine instructions from the CPU to main memory. So sometimes, well, you're normally fetching your instruction from memory. Address bus, 16 to 40 bits wide electrical pathway. Now, in this course, I don't talk about virtual memory much. And if I do, it'll be very briefly. But it becomes very complicated because, why is it only 40 bits? Well, if you remember your orders of magnitude, right, 2 to the 30 is approximately a gig, right? So you have like 2 to the 10 times 2 to the 30 equals 2 to the 40, right? So 2 to the 10 gigabytes of memory, of real memory. Well, that's out of hand. That's not, you're not going to do that yet on a computer, most computers. So you only need 40 pins coming out of your CPU. However, what virtual addressing is the CPU, the operating system and all the applications thinks it has, the operating system thinks it has 2 to the 64 bit, which is 2 to the 32 times 2 to the 34, 2 to the 32. Which is huge. And you don't need that many pins coming out of your CPU, but you want to give your programs the ability to think that it has it. So you have actual translations of every address through virtual address translation, lookup tables, and you actually cache those too through a translation look-aside buffer. Or a program inside of IBM to do this kind of thing, to test actually the hardware that does this kind of thing. It's complicated. It takes memory addresses generated by CPU to address memory locations. So the address bus. And then read-write controls, wires from the CPU to memory, which signal to memory when read or write is happening. So this is very conceptual, right? You should commit that to memory. And if I ask you to sketch that on a test, this is the conceptual computer architecture. Now, we're going to see a minimal computer architecture in a minute down here. So we're going to go down to the next thing now. This is a longer lecture. And it has introduction to computer architecture, also microprocessors and microcontrollers. We're going to see this minimal computer architecture in a paper I published when I was a professor at Purdue, 98, 99. And then a very brief skimming through robotics in IBM quality control. And then these two readings here, I haven't assigned those as readings for class discussion because I'm going to cover them here. And it's really just an introduction. In advanced classes, we dive down much deeper into those. So let me make this formatted nicely for just using a PDF instead of a PowerPoint. The bigger, and this browser behaves nicely for going forward. So yes. Levels of computing. Now, a lot of this things and terminology I have invented myself. Now, it's not weird. I mean, there's similar things other people do, but the minimal computer architecture, conceptual computer architecture are things that I've coined. Also controlled randomness that I'll talk about with IBM research. These levels of computing I made, but you can find parallels to this in other people's lectures and textbooks. And these are whole sectors. These are whole careers. These are completely different kinds of jobs, computing jobs. But so we have embedded PC, PC server, workstation, mini computer, supercomputer. And so what do I mean by that? Well, first we're going to look at the architecture of them. And now I'm going to describe what these acronyms are in a second below. SMP is symmetric multiprocessing, used to be shared memory processing. There's one memory, multiple processors. MPP is like a computer network in a box. Every little processor has its own little memory and caches too. That's massively parallel processing. And vector register is where you have multiple functional units to process vectors. If you've done any linear algebra or matrix manipulation, you know that multiply two matrices, it's a row times a column, dot product kind of vector operation in that case. And so we'll define that a little bit more. Oops, I want to scroll. Center it nicely. Button push. Okay, next button. So what are these things? Embedded systems are for real-time control, for automobiles, appliances, factory automation, aerospace. A PC, you know what that is. We all have them, PC server or workstation. Well, that's a little bigger. So your servers, and systems made for doing CGI kind of things. So VLSI circuit design, very large scale integration, integrated circuits. The animated TV movies, the animated movies that you see. You need a beefier machine, essentially a beefed up PC, but it can be, 5, 6, 10 times as costly based on the power of it. And then a mini computer is essentially a scaled down version of the SMP supercomputers. And the task serving supercomputers, old mainframes that evolved into much more than a simple mainframe. It's a local area network serving up to 500 people. Also wide area networks or internet servers for supercomputers. SMP are also lands, but for thousands of people. Air traffic control, New York Stock Exchange. And this is mainly what I worked on inside IBM, although we had a vector register unit we could connect to it. We could connect to other kinds of machines. But they were $1 million machines, and they were used for air traffic control, New York Stock Exchange, running countries, military infrastructure, highly secure hardware and software systems, and highly fault tolerant. And then vector register is for matrix intensive grand challenge apps. So you can Google the grand challenge apps. I was going to do it in here. I might still do it, but you can see what's defined there. So you can imagine astrophysics or the human genome. These big grand challenges lend themselves to a lot of linear algebra, matrix manipulation. And MPP too. So, the human genome actually was used with large networks where you borrow a CPU time on everybody's CPU all over the place. But you do a lot of the grand challenge stuff with vectors. And then MPP as well, and also some application-specific things, chess. Characteristics now, I've had to change these costs over the years, but the relative difference stays pretty much the same. Embedded systems are usually pretty cheap, although they're not always cheap. I mean, if it's in military systems, it's not cheap. But usually small and can be extremely fast, but typically not. I mean, your phone's an embedded system, and now your phone costs $1,000. So, go figure. It used to be that phone was wasn't a handheld device for most of my life, but now it's a computer. Embedded systems may be also hardened for industry or space. So all the physical impacts that can happen in a factory, as well as gases and temperature changes. And space, also radiation, bombardment, solar radiation. We're lucky we have an atmosphere, or else we'd be bombarded into a not so nice state of health. PC personal computers faster than typical embedded, but otherwise relatively slow. That's not always the case, because some of these embedded systems, it's a warhead of a missile or something, it's going to be super fast. PC servers, but most of the embedded things are cheap. Most of the microcontrollers, billions and billions of them. I asked a student when I was at Purdue in 1998 or 97 to look up how many microcontrollers there were at the time. And there were billions of them, like more, there was I think it was 10 or 12 billion. Only 7 billion people on the earth now. And back in 97, it was probably 5 billion. And there aren't that many PCs. Maybe now we've gotten up to the magnitude, but there's more microcontrollers, and they keep making microcontrollers. There's more of these simple devices than any of the others. So, so PC workstations faster and more expensive. Mini computers, you can run a simple network on a regular PC, but 100 people, not so much. Mini computers, very fast, 500 people servers there, and you pay $100,000. Extremely fast supercomputers, $1 million to 10 million. And I haven't checked the prices lately, but it still seems probably correct enough. And then example devices. We're going to drill down a little bit into these, but this is an introductory lecture, so I don't expect you to know any of these things in great detail in this course. Microcontrollers and microprocessors, you're saying, what the heck's the difference? Well, we're going to look at that in a second. But microcontrollers are meant for embedded systems, and they have, and we'll see, they have timers on them, they have special ports, special bit control, also motor control pins, things, different things. Microprocessor is more powerful and is not meant to be embedded in most cases, although now it's getting embedded quite a bit. And there's different flavors, of course, Intel, Motorola, and PowerPC chip. I won't repeat the story here in length, but when I was at IBM, we developed the PowerPC chip. Now, I was in New York and coordinating some things in Texas from New York too, but in New York, in the main research and headquarters, everything's centered in New York, IBM. But there was a plant in Burlington, Vermont, I could have gone to and worked on the PowerPC chip. This was an attempt, a successful attempt, to help Apple run DOS, Windows kind of applications. And you say, why would IBM do that? Well, IBM never cared about PCs that much. I learned firsthand from one of the senior executives that it was never more than 10% of the revenue. PCs are just junk machines. And so the PowerPC chip was actually developed to help Motorola and Intel keep the markets alive, believe it or not. And it was funded by DRAM sales. IBM made its own DRAMs. And then there was dumping from certain countries, I won't mention which, but they're dumping where they dumped DRAMs onto the market at really below cost prices, and it kind of hurt IBM. And so IBM had trouble funding the PowerPC chip, and they found funds elsewhere. But it's a weird kind of path. You wouldn't guess that unfair trade practices would hurt DRAM sales, which would hurt making the PowerPC chip by IBM to help Motorola and Apple, because Motorola was a processor and Apple at the time, compete with the Wintel machines that then had dominated the market by the mid-90s when I was, okay. So application-specific integrated circuits and programmable logic controllers, we learn about these in details in other courses for device control and specific things. PCs, microprocessors, we all know about Intel, of course, and AMD is just another flavor of Intel. It's essentially the same instruction set, different architecture, different implementation below the hood, but it's doing the same instruction set, machine instruction. Motorola is completely different. PowerPC chip was completely different. PC servers also, Intel, and then you start getting workstation class things, the MIPS I didn't put up here, but Spark processors, Silicon Graphics terminals, Sun or IBM RS-6000 workstations, which helped a little bit with in Texas via IBM New York. I supervised a young engineer to port some of the stuff we were doing to systems down there. Sun I used in the beginning of the 1990s, and that was multiprocessor systems running very large scale integration development when I was a PhD student. And we used Sun also in the AI DuPont Children's Hospital. Mini computers, AS400. I didn't directly work with them, but some of the stuff I developed went to that. Amdahl's competition there, HP, Hitachi. Then supercomputers, the System 390 was where I worked, and with other people. Vector Register, Cray is known for that, even though we couldn't do that with the System 390. MPP, the IBM SP2, I believe I talk about that down here in a second. Power of the Deep Blue, it's a footnote now, but and now attempting to beat the computer at Go, which is a lot more complicated than chess. It's not possible. But the first to beat anybody at chess, Grandmaster, was an IBM machine. It says that right down here someplace, somewhere it does. No, maybe it didn't, but the Deep Blue was IBM Power Parallel. And that was a group within our building, our complex of buildings, a bunch of buildings in a compound, very secure compound. Helicopter flying around, had to gate into the compound, gate into your individual building, card into your buildings, card in through the gates, and then special access to test floor that I had to researchers. The Power Parallel was a group of MPP application-specific chess playing group that made a machine to beat Kasparov, and it did. He actually gave up after a little while trying to beat the machine. That early 90s. Operating systems, embedded systems, sometimes there's none, and that's good. You don't want the overhead. Or a real-time operating system like we have on the Mars rovers, and we've had for a while. And so you don't want a lot of overhead. You want it as simple as possible. Just get the basic jobs done. And you can have often no operating system for air conditioner or a refrigerator or a fuel injector. PC, we have a whole host of operating systems. You probably learn about an operating systems class. I believe all of you take that. PC server, workstation, Windows, NT, that's not around anymore. Well, maybe it still is. You still have to pay a lot to get the kind of user support. They charge you like $200 an hour to get user support, because this is, that's long ago. Unix and Linux, of course, so you probably know better. Red Hat, IBM actually bought that for I don't know how many billions of dollars, but AIX was IBM's version of Unix that we worked on, our 6,000 workstations. Then the mini computers run all these other things. And then so we actually had 12 operating systems at IBM that we were using when I was there. Different things for different reasons, internal ones that are sold to customers. And then we wrote our own, had 1.5 million lines of code for testing the supercomputers. I, of course, didn't write all of that. I wrote 20,000 lines of code, but I was not a coder as such. I had to do that just to implement the research that I found it so that it could get into the APIs for the systems programmers to use it. And then, custom OSs for vector register machines. Oops, I just hit the button here. Now we want to talk about microprocessors versus microcontrollers without diving down too deep into this publication that you see at the bottom here that we'll look at briefly. And the stuff in red is the most important. So we have CISC versus RISC. Now, most microprocessors around 1990-ish strive to become more RISC-like. And there's more to RISC than just simpler instructions. The idea with RISC is that programmers for decades were not using the power of the most complicated instruction set. And so it takes overhead to maintain that large set, to decode it. It's a long, bigger opcode, first of all, but there's lots of extra hardware. And so the idea was, let's try to make it so programmers have less instructions, use the ones that they use most of the time, or implement the ones they use most of the time. This is in microprocessors too, but it's really profound in microcontrollers. So I'm just clouding it here a little bit, but maybe I shouldn't talk more about that, because we actually have, I believe, a lecture where we dig down into that a little bit more. But just understand there's more to CISC versus RISC than black and white. Both integer and floating point calculations. So I had been assuming that all of you know what floating point is. Now you have floats and you declare them in your code, but I'm not sure many people, I haven't seen a lot of people really understanding how they lay out in the machine and where the mantissa and the exponent are in the actual bits, and how that's put together. So we have a lecture coming up on that. But floating point, as you can imagine, it's scientific notation in binary, something, 1 point something to times 1 point something times 2 to some power. And so, that's going to be more complicated than to implement than integers. The idea of a microcontroller, very top in the big red, intentionally simple for single chip embedded applications. Large address space with a microprocessor. You can fit everything in that hardware architecture, data and your code on the chip itself. So you don't have separate, it's not a motherboard, it's a chip itself. And then, on-chip device control, digital analog conversion, analog digital conversion, pulse width modulation for motor control. I'm not going to quiz you on that. But I'm not going to expand all the acronyms. I'm not going to make you memorize ones that are probably somewhat obscure for most of you to know in an intro class. Now, I do want you to now know different these acronyms. So there's no acronym here, but this is a simple single processor. And we're going to have a lecture on cache, just the basics. Take advanced computer engineering, we have a couple of weeks of that. But you have memory and you have a processor, and then you have a cache. And without going into the cache lecture right here, the idea is you anticipate what you need. The processor anticipates, the cache anticipates what you need based on usually what was least recently used. What most recently used by the processor, you had to go to your memory to get it and put it in the cache too. And then if you need it again, you can get it quicker out of the cache than you can out of memory. And that's the basic idea. And that's because you have static RAM in the cache, it's faster, more expensive, and the memory's not. So that's all I'm going to say about that here. It gets a lot more complicated that with multiple layers of cache, instruction versus data cache, shared caches between multiprocessors as well as dedicated ones. I don't want to cloud that up here. But I do want you to be able to sketch this. And there'll be a review in this intro class. I actually post a review that tells you which slides usually, so you can see that on the website. I'll do that again. Don't look at it yet because it's from a couple of years ago, and I will change it. Symmetric multiprocessing, also called shared memory processing. So SMP, yes, you should memorize that. That should be part of your lunchtime chat, interview chat thing. Somebody says SMP, oh yes, of course I know what that is. And so you have processors out here, and they're all sharing this memory in the middle, and they all have to go through caches to get to it. Or they'll look in the cache first when it's not there, and then get it from memory. But the idea is you share memory. Now you could say, well, that's going to cause a problem, isn't it? Yes, it can. So there's a whole cache coherency policy. I bought a very expensive book at IBM and wrote a program just to work on this kind of stuff, because it's not something I'm going to summarize here in this lecture, certainly, but it's very complicated to make sure you have coherency You don't have two processors changing the same piece of data at the same time that both share a place in memory. Vector register is like this. So you have a processor, cache, and memory, and you have multiple functional units in the processor for arithmetic and logic and other things, and multiple data elements. And so it's a parallel thing. Vector register. You should be able to sketch these. And then MPP. So if you just think of how a computer network works outside of the box, it's essentially a network in a box. There's different interconnection architectures, typical networks. It varies. We actually had dynamic optical interconnect for crossbar switch for IBM external to the big machine. But typically inside, or typical PCs or even all over the E-Town network, you have a static network. It's a fixed architecture of where everything is. There's dynamic ways of doing it too. We don't drill down into that here. That's more for advanced computer engineering. The basic idea is a network. So this is now inside of a computer, one box, massively parallel processor, where it has a bunch of processors, but they're not, there's not a shared memory here. You're not going through caches. Each processor says, I'll take care of talking to the other processors. I don't have to worry about what's in their memory. We actually do at times because you have to synchronize and you have to control how all this works. But this particular kind of machine, it's like a computer network where each PC is doing its own thing. In this case, it's each processor or core. And you can interchange core wherever I say processor here. I mean, cores on a chip now are the same as processors. Right? And they're all SMP for the most part on the PCs now, up to 12, I believe. So, conventional ones now. Large network dedicated to a single test. It's the same thing. I mean, it's the same picture, except in the box in the middle, you have an Ethernet or an internet or intranet. At IBM, we had an intranet. So we had our own optical lines leased between the cities and the ocean. There's 450,000 people on that stuff. And so when I communicated to and supervised somebody in Austin, Texas from New York, we had secure communications because we didn't use anybody else's system. And it was hardwired at the time. Optical connections, broadcasting over the internet, proprietary confidential development of machines. Now, you've all had programming before. You got programming before you come into this class. So you understand numbers ranges. Maybe you don't know about signed and unsigned numbers or two's complement. We'll talk about that a little bit in here, but I test you in here on that. That's more for hardware design. And you can imagine if how many numbers can you do with 8 bits if you don't have a signed bit, right? You can't do negative numbers. Well, it's 0 to essentially 2 to the 8, 2 to the 8 minus 1 because you got to count 0 as one. And then if you have a signed bit, well, you have less. It's the same range of values. I mean, same number of different values, but you go from 0 to 255 if there's no signed bit, and from negative 128 to 127 with signed bit. And 1632, 60 n bit, same thing. Now, floating point, and I guess at this level of class, I just want you to appreciate the magnitude of these numbers. And we're going to have a whole couple lectures on floating point action. Some examples. We've even had homeworks in the past, but we'll just have examples probably this time. Look at the size. I mean, if you don't understand the magnitude of these numbers now, you should learn them. So we did the orders of magnitude stuff, right? And we went up, 10 to the 30, 10 to the 40. Okay. Well, look at this with a double precision, double float. 10 to the 308. Well, that's borderline absurd of a number. But, you're doing grand challenge stuff, you may very well go there. So your machines need to be able to do that. Here's integer number precision. Okay, well, the smallest number is 1, it's an integer. Floating point, single precision. Now this is the, what's this here? This negative. This is the fractional part, the mantissa. This is the number. We'll come back to this. And there's a different talk when you talk about precision versus the range of numbers. They're actually two different things. It's probably not clear here, but it will be later. Okay, here's one of my inventions 24 years ago. Minimal computer architecture. Inventions for teaching purposes. The invention stuff I signed over with all my intellectual property at IBM. It's there. You're not the neural network chips and stuff before. I'm a teacher, so I'm not looking to make money on any of that stuff. Choose that path. Actually, could have when I was in the development world. I passed up some opportunities in my 20s. Minimal computer architecture. So let's stare at this for a second. And on the review sheet, I'll tell you, like, this is slide number, whatever it is, 16. I've had in the past say memorize it, be able to draw it, because this is a key thing. So I don't want to go too fast over this. And this can apply to pretty much any machine. That's the idea of the minimal computer architecture. It's not minimal like in terms of simplest. Probably I should clarify that. It's minimal in the terms of you can apply this abstraction to any scale machine. Most supercomputers down to embedded systems. Assuming you have some instructions and you have some hardwired thing that doesn't even have computing, a CPU in it, but an embedded system. But assuming you have some kind of processing going on, you have a program counter. It's actually a piece of hardware, and we'll learn about why things are automatically incremented or not. It's I can tell you right now, it has to do with spatial locality of reference, and that means that the code that's in memory that you're fetching, and this program counter is a pointer, a piece of hardware pointing across the address bus at it. And when you execute, in the pipeline, when you do pipeline design and implementation, you're going to fetch an instruction, and this program counter is going to point at it. And then you want to automatically increment in hardware while this thing's flowing. As soon as it gets to where it's going, as soon as you free up the lines here, you want to start pointing at the next thing. And you're saying, well, what if it's not the next thing? What if you're in a programmed flow and then you're jumping to a subroutine, just jumping somewhere, or which you can in your code, right? Or you just subroutine call or function call. Anytime you do that, what that looks like in machine code is you have some indirection, and you're not going then sequentially any longer through the code through memory. So, but in all probability, this is why probability is so important nowadays in computing and is assessed as such. It's a program counter because in all probability, you're going to need the next sequential circuit because of spatial locality of reference. We'll talk about this when we talk about caching. But right here, this is why this is a program counter, the pointer. So program counter to address instruction to be fetched from memory. An instruction register to put it where you should get it. So point at it, get it, put it there. Control logic to create all routing signals after decoding and fetching. So that's a whole part of a course, or a whole course. Some of you had 332 class. That's all your add or subtractors and your finite state machine design and pulling all the strings. It's not show every possible wire here. There's thousands, millions of wires, but there's strings coming out of this control unit that make everything flow. And then the ALU, design this in other courses, adder, subtractor, multiplier. There's lots of stuff in there. And for manipulation of data instructions. So you get stuff it in there, you do something to it, and then you put the results someplace. Registers for storing intermediate results of calculations. This is what I was alluding to. Didn't draw it in the conceptual computer architecture, I mentioned it, that in the CPU, you'd have these pieces of memory that are really fast, and you would hope to keep all of them in there. And actually part of the whole RISC design paradigm shift in the early 1990s from CISC to RISC and everything. Again, it's most microcontrollers are mostly RISC, more RISC than processors. But part of that paradigm shift to RISC was putting more registers in the processor, because if you're going to have less instructions, then it would behoove you. I've never used that word in a lecture before, but it'd be good for you to have a lot more registers, because you don't have as many powerful instructions dealing with memory, and so you want to keep everything close. Okay, so a status register for storing status flags and condition codes. So whenever there's an operation of some kind, you're comparing two things, loop count to figure out if you're fall out of the loop or not yet. I mean, so you're comparing, the loop count to whatever the loop presently is at, and then if they're equal, a flag will set in here. Or, you exceeded whatever flag would set in here. Well, actually, the equal flag. And then the next instruction would be, jump someplace, and that it would know to look in the status register as part of the programming of the control unit in hardware microcode, not assembly language, but there's actually programming of the control unit. We're not going to get into that here, but something's making all this stuff happen. Where you can actually hardwire it too, which is another thing that RISC processors did for a while. There's also a condition code, or status flags and condition codes. There's also control flags in here. You can change default register banks and things like that. But we don't want to get into that here. And this can be as many as 256 bits at IBM, because we had all kind of configuration stuff, as well as passive reading of status from 1400 instructions. Memory, as we already mentioned, for storing data instructions, and I don't make a distinction here between the Harvard and Princeton architecture. A stack for storing addresses or processor stats. We're hanging around this picture here for a while because I want you to know it. So a stack, and you know that from data structures or your intro programming, that you push onto a stack and pop off of a stack. Why would you do that? Well, if you are jumping, or a program call or function call, and then you're changing what you're pointing at, you jump into some other code segment. Before you do that, you have to stuff onto the stack the state of the machine. You got to store the program counter so you know where to return to in your sequence of code, and branched away someplace. You want to store the status register because you want that data to be valid when you come back from your function call. And so you stuff all that on the stack, and then when you return, you pop it all off. And interrupts are serviced the same way. An interrupt is a hardwired physical line, electrical line, coming to a processor that says stop and give me service. And we've learned about this in other courses if you had it with me. Well, some of you have not. So, but you vector off to an interrupt service routine, and you deal with whatever it wants, whatever the peripheral wants. I/O, which in this minimal computer architecture is addressed as memory. So this is what a PC typically does, and most simpler devices until you get to large scale systems, is the stuff that's connected to the motherboard, the I/O, the boards, the graphics cards. Well, there's different kinds of communication sometimes with that, but you treat your peripherals as if they're just pieces of memory. And so the CPU doesn't distinguish. And then you just have to keep track of that. Make sure that if you put a new card in, you're not stomping on something in the memory. You used to have to do that. Now it's all plug and play, and the BIOS will figure it out for you. You used to have to say what address range your card is using before you plug it into a slot PC. All right, that's more than you probably wanted to hear from that particular little slide. But it's important, and you will need to know this. I don't have a review sheet, but typically in this class, this is where I want you to memorize it. Now, the microprocessor versus the microcontroller in simplified terms. The microprocessor has memory off somewhere on the motherboard. The microcontroller, the memory is in this one chip. That's the easiest way to just show it, just like this. Now, this other stuff, of course, caches and things that aren't mentioned here. Microcontrollers don't have them, microprocessors do. But in simplest terms, you know, in an intro class, this would be a nice thing to just say. I could give you this picture. Draw a box around the microprocessor. Let me give you the picture again. Draw the box around the microcontrollers. Then explain, or we don't even have to explain, really. All right. Now, this is important, and this is the heart of computer hardware design. The time it takes for a task, machine instruction task, you know, assembly language code. I mean, it goes for the high level language too, because it goes down, equals the average cycles per instruction. We'll talk about that in a second. Times I sub c. That's just the number of lines of code. So you can imagine time's going to be more if you have more lines of code to do the same task as you would otherwise if you have less lines of code. And then times some representation of the speed of execution frequency. It's actually to make the units work out. This tau is 1 over, you know, that symbol at the end there is equal to 1 over the clock frequency. Now back to the CPI. This is more tricky. The average time to fetch, decode, execute, and store results for instructions. There are many strategies to decrease the CPI. For example, processing several instructions simultaneously. Super scale. We'll look at this briefly in this class. That's parallel pipelines. We don't even know what a pipeline is yet really in here, but parallel pipelines. So he's fetching 2 instructions or 3 instructions at a time, 2-way, 3-way super scale. Moving data directly between IO and memory. Again, we just mentioned it here. Don't talk about it next. Look in detail in advanced classes. Direct memory access, where the processor or you free up your processor. Like your IO can get to the memory that belongs to your processor without the processor caring. I'm saying knowing. I mean, it knows, but it's not being tied up. Also reducing CPI. Hardware to anticipate and take pre-actions. Not only pre-fetching data, instructions, and caches. There's a whole lecture on cache. Well, you know, a brief lecture in this class on caches. So, you know, anticipating, but also pre-fetching branch target addresses using branch history table. Or so, you know, if you've been branching someplace before, wherever you branch, when you branch, and you figure the address that you're branching to. And if you remember, I mentioned virtual addressing. That actually involves a virtual address translation too. You want to cache that as well. 2 different kinds of caches. You're caching the branching, you're caching the virtual address translation. And these aren't the caches that you're thinking about when you think of caches. Those are data instruction caches for the programmer execution use. I mean, this is program execution use too, but this is inside the internal hardware. You don't have access to this. Now I wrote a whole thing testing branch history tables at IBM, and also another one for virtual address translations. It was part of the development projects I had. It wasn't the research part. But I mean, it's still difficult stuff. Other speed up techniques include reordering and optimizing instructions out of order execution. And that's becoming more and more of a thing now. When I was at IBM, there was somebody there in our group, actually came over from IBM Germany, that was doing that, some of the very first of that in the mid-90s in the big machines. Now you see it, not only see it now in processors for many years, but we're also using neural networks now for prediction. And why would you want to do that? Well, if you have parallel pipelines and you have all these instructions executing simultaneously, one instruction might depend on the results of another. What if that instruction you're depending on is in a parallel pipeline doing its own thing, and then you got to wait for it to get done? Well, there's ways to unravel all that and reorder the instruction execution so you don't end up choking pipelines that are parallel to you because you're waiting on each other. Okay. So who does this kind of stuff? Computer architects, computer engineers, more than anybody. Not electrical engineers, not computer scientists as much. This is computer engineers specifically build all those things. Now, the group I was in, you had the minimum of a master's to get into. And so, you know, you're going to really design the systems. You got to work your way up. What about I sub C? Well, everybody codes. Engineers too, maybe not as good, but computer engineers should be as good. But you know, other engineers maybe sometimes not as good at programming. But anyway, this is what you're doing, dictated by engineers and programmers and how they code, you know, high-level language assembly or whatever software. It all factors down to the number of instructions. And then this is not really any of you most likely, because this is the device physicist. So this is a whole field in itself. This is more electrical engineering. This is more physics. We touch on it in my classes. The computer engineers have learned from Dr. Strada and others in the past about this. But this, if you're going to do this kind of thing for a living, changing the clock frequencies, that's material science, electrical engineering, material science. So most of you are going to be concerned with the middle here of coding, but should be aware of this is the main thing going on. And there are people, some of you, presumably in the future somewhere, would reduce average CPI. And so for most applications, you're not tweaking the CPI. I mean, it's fixed, it's been optimized, it's been tested, it's been developed, it's hardware. There can be software related things, but for the most part, most applications I see. Yeah, the coding matters for all of us, I should say. This is something for other classes, but it's thrown in here. If you want to see the code difference between a microprocessor, this is from my publication where I'm showing something done with a microcontroller. Now, this is 24 years ago. This is 68,000 microprocessors. They were in all the Apples for a long time. The first HP calculators had the 6800 in there. Then Motorola went into cell phones. And Motorola's still a thing. It's a great company, and really beautiful, well-designed machines too, but just didn't keep the market share. And Apple switched to Intel processors, which certainly didn't help Motorola. Here's a microcontroller. So this is microprocessor versus microcontroller. Well, there was a lot more lines of code for the microcontroller doing some tasks, but you'll see that the actual number of cycles is less here. So, or, you know, is something to consider, again, for other classes. Also affecting I sub C. This is making a crack. And I love LabVIEW. I've used the heck out of LabVIEw. I mean, sorry, not LabVIEw, but MATLAB. LabVIEW wasn't my favorite. Our robots used them for a while, which I'm going to glaze over super fast here, some of that. It's not good code, in my opinion. It's really easy to use, and people argue, oh, we run this at the super collider running with LabVIEw. And somebody had to teach a whole course in LabVIEw for many years, and it was actually the second analog course instead of electronics, device physics, or power, the way it was over the past different times, different professors over the past 20 years. It's not good code. it doesn't scale well. It's not good software engineering, but it's super easy to use. So you want to be careful of that trade-off. MATLAB is not super easy to use. It's easier than doing your own code, but super powerful. I love MATLAB. I love all toolboxes. The deep learning neural network thing, which I got for the college 23 years ago. I got MATLAB first and then neural network toolbox right after. Maintainable, scalable, so here I'm ranting about LabVIEW, how it doesn't scale so well. It's not good code. But again, it's so powerful. People use it. So do you want things to be super easy for yourself, but then if something goes wrong, nobody knows how to fix it? That's the gist of it. You could read more in there. Now this is from robotics class that I teach. This is just showing the simple embedded systems that are in different robots. And I didn't update this. Now we have other robots that have been up there. A very successful one. I just talked a whole bunch last year in this course as it landed and deployed to the helicopter and everything. You can look at how simple those machines are. And inside NASA, that's a task. Keep it really simple because it's just got to do the task. And you can't send somebody to fix it. It takes up to 20 minutes just for a radio wave to get between Mars and us sometimes. And at least 6 months to 2 years, depending on whether Mars and Earth are synchronized all the time to get people there. So, it needs to be fully autonomous, and you can see the publication down there. And then very quickly, this is a robot we've developed and competed in the ground vehicle competition in Michigan on a big military base 3 different times against up to 60 schools. Only one other one was an undergraduate group. Most of these are big graduate groups with $1 million budget. But we held our own. Thing is Contact Company, perhaps our best friends, corporate wise, hired at least a dozen of our students, more than that by now, plus track, and gave us quite a bit of money and parts for our robots. So you see his contact thing now. I'm going all the details, but this is all of that, the vision system, that was the whole thing there. The guy kneeling down on the right over here did a whole thing on vision, did a summer research thing at the University of Florida, got a job with Intel, and then Google first and then Intel, and Intel paid for his master's at Stanford University in electrical engineering on image processing. And then this guy here, we went to Italy together. He presented the research on mapping techniques, and then he got his master's and PhD, and now he's leading a research group down at Johns Hopkins. This guy running a company with his dad, taking over this. This guy went into an automation group company. This guy kneeling down has been at Lockheed Martin doing top secret stuff for a long time. It is fully autonomous and global positioning and everything. So this is just an overview. This is kind of thrown here. I'm not going to test you on any of the robot stuff here. There's LabVIEW, which I was reluctant to use, but it gave you really beautiful modeling of things. We made our own wireless communication to the military standard. It's like TCP/IP, but it's for coordinating tanks in the field. If anybody's spying on this, this has changed all the time, so I'm not disclosing anything here. But we're giving a military protocol to develop too. This is if you've done networking, this is a packet and how it breaks down. And we were only one of a couple of schools that actually made this work. And the PDF, if you're watching this on YouTube, assuming I'm posting this on YouTube, the PDF will be linked below, and you can get to these links. I'm not going to put all the links in the top of the YouTube video. And then this whole evolution here, 0 and 1, 2. They named it Wonderbot. Simulation versus real-time control. This pause a second here. So simulations are usually much more complex and running on not the real-time robot or military thing out in the field, although nowadays some of the more sophisticated things will be running simulations. Certainly fighter jets will on the tanks, but smaller things not. The simulations is running separately, and you want it to interact with the real-time code and give it a better physical model, improve the physical model that it's learning as it's sniffing around, like on the surface of Mars or in the battlefield or whatever. The real-time codes initially, well, I mean, it's simpler. It's supposed to be simpler hardware, simpler code, and you want to interact with the global. And this should be a nice pairing. So if you have a Mars rover, you could run a simulation on the landing vehicle, but it's typically not. The simulation is usually running back at home, and then you're like triangulating with satellite imagery and ground-based stations and plotting the thing, sending information to the rover about what's ahead of it based on observations from far away, and then the rover tells you what it's bumping into, and then that's fed back up to the simulation and builds the environmental map in the simulation. So it's a concurrent thing. And the same kind of thing goes on in fighter jets. We're running a simulation of the Earth, or maybe even the other fighters, what they're potentially doing that you might be in a dogfight with or in a squadron with your buddies. So you can drill in all that. Again, this is for robot class. And then I go very fast through this. This is the IBM, some of the IBM stuff I did. So we wrote our own custom kernel, I wrote the APIs, and we tested parts of the supercomputers, up to 512 processors in a Coke machine size box. But we test a board at a time, a processor at a time, and we'd have 20 processors on a board. 2 of them were dedicated for IO, a whole different instruction set, and the other ones are general purpose ones with 1,400 machine instructions. Typically processors, Pentiums and Motorola's, whatever, like on order 700 at the most. So we had 1,400 at the time. And then we tested in 3 environments. We would actually simulate the prototype architecture machines, which was tricky when 64-bit architectures came out. We had to simulate on a 32-bit machine and then run our test kernel and threads and my APIs and everything, and the whole paradigm on top of the simulation. And then the VLSI guys would build a chip and circuit simulation, including analogs and digital testing of all that. And then we would run our verification on top of that. And then we'd prototype a chip, and we test on top of the chip. And you could get different results each time, believe it or not, because your circuit simulation can fault. You get so it's too small. It's one thing I would talk about. It's not really a topic in this class, but an IBM we had where the verification, everything passed on the simulation of the architecture. It passed on the circuit simulation because the PSpice and the logic simulators didn't take into account that the feature sizes had shrunk and the clock speeds had increased to where this fast switching wire that was really thin and next to another fast switching wire, this one wire was inducing errors in the wire adjacent to it. And the only way that was discovered was actually when the chip was fabricated. So you might say, oh, well, it seems redundant. I said, no. And here's a case right here where we caught an error that only showed up in the physical built thing. And you could say, well, that's a fault of the circuit simulator. But not so much, because, it's tricky to build that into the SPICE analog circuit simulator. It wasn't SPICE, it was an IBM proprietary thing. And then so you could see more here. And this is, I'm not going to go on this, but this is how the code works. And so there's multiple random number generators. And so it's not just, random number generator, just pick this one thing and write it now. There were 7 different ones, and they had about all these different qualities. And I had some of them had to go backwards so we could find errors. I had to derive backwards multipliers for them. And first I had to research all these different kinds. And there's a seed generator and a pass generator. So different passes evoking of different threads concurrently one after another. Where there's a seed generator that generates the initial seed, with the pass generators that then can randomize data and control bits for indirection and everything else. And this is all terminology. I'm not going to go into it here. And there's pass generator, and there you can see the seed generator on the left, and then the pass generator on the right. Successive passes, n number of passes of threads, and then seed generator qualities, pass generator qualities, and then I assessed the different qualitatively and quantitatively these different random number generators. And and some of them were like combining two generators together. These Fibonacci ones, you have to have a separate seeding array that you randomize with another generator, and then you pick an initial seed out of that. And that's not the seed generator. There's a separate seeding thing just for the pass generator, and that just adds to the quality of how random it is. But then there's other problems with speed and things. So I don't go into all that. You can look at all that. In controlled randomness backbone, so they patented this. This was my whole idea. And I wrote a user manual for all of them. You could find all that down here somewhere. Yeah, click on that. You can look at all that. And then actual code, if you feel like going there, see what that. This is PLX and System 390 assembly. It's like old Fortran, but with case statements like Pascal. Okay. Oh, okay. So that was an hour and 15 minutes. Let me, for the students' sake in here, go one more place. So in Canvas, this is what the students use. The syllabus is on there. We have videos. We did stuff with transistors and chips. I'm not going to put these other Moore's Law or Intel versus AMD because that was last year video. We just looked at stuff having to do with AI things, and where there's automated journalism. The AI is writing articles, and then another case where the stock market is doing automated trading based on these machines. And then there's a whole bunch of other videos here. These aren't published, and probably won't, because we had a guest speaker last year, a cousin, my nephew actually is a submarine commander. And so we did stuff around that. And then GameStop with a short squeeze, and that was last year. Not going to do any of that. And I may post some other things here. But one last thing for the students, you have assignments coming up. We just did one, and it was only 10 points. A couple of people didn't do it, and it's past the discussion time, so I can't really give any points on that. You could argue maybe and submit something, but you have 1,000 points total. The idea is when we have a reading thing, like this one coming up in 2 weeks, or next week, I guess, we have one due tomorrow, which is you pick a stock, and we've already talked about that. And this is picking a company that you want to work for as well as invest in, so understand its corporate culture. Now you're just picking a stock here, so it's not worth a lot of points, but you're going to have to defend the pick of this, and you're going to defend why it went up or down by the end of the semester. And don't expect to have to beg for mercy too much if it goes down a lot. I mean, the market forces are out of your control, especially if things internationally happen or the Fed does something weird with the interest rates, but that's already been compensated for. And then this national security policy thing. So I know when we talked about, I gave you a skim over article in the last talk where it wasn't part of the main reading, but if you really wanted to talk about the Ukraine and all around that, you could. And then I found when I read and graded the assignments that I think there were 4 of you that were very interested in that. And that's the one you picked to write about. So that's not why I'm doing this. This homework, actually, this lecture by a U.S. Ambassador Craig is on the syllabus to do, but I want you to do it on your own outside of class time as part of the homework thing. You got to listen to it. You can consider it an actual lecture. It takes time to do. First, you want to find out about Ambassador Craig and where he's been, what he's done. He's been, in 2 White House administrations and running things in Bogota, Colombia, and Damascus, Syria, and all kinds of things. Vice president of Boeing Aircraft, also runs his own venture capital company in the Middle East. You want to learn about him and list stuff like this, and then listen to this very carefully. It's 40 points. Right about that. and then read this other article here of, it's kind of funny, but interesting as well. Somebody he got hacked by the North Koreans. He was a professional security programmer. By the way, we're going to have a guest speaker on that coming up. And so he took down North Korea's internet himself. And no credit can be earned after all. This is discussed in class. So this is 60 points now. So you don't want to miss that. Right, so that's 6% of your course grade. You don't want to get a 0 on it. But it's not fair to give credit after we've discussed it in class if you weren't prepared, because you just, like, I'm going to show what everybody's done. So please do that. Okay, so let's stop sharing here. And it's like everybody was here, which is good. Speaker again, we gotta stop recording now. Oops.